Okay, so we're finishing up lesson 4.2, but we're going to do a quick recap first. Okay, so we talked about Rolle's theorem, which was really just the beginning of the mean value theorem. And what the mean value theorem says is if you have two endpoints on your domain, and you find the slope between those two endpoints, then that same slope will occur somewhere, at least one other time, between those two endpoints. And so Rolle's theorem said that's true if the slope is 0, but the mean value theorem was extended to say, you know what, it doesn't matter what the slope is, it's going to happen regardless, whether it's positive, negative, or 0 slope. So that's what the mean value theorem says. If you take the derivative of the function, and you set it equal to the slope between those two endpoints, and you solve them, then it will tell you where this slope occurs between points A and B. Okay. And there may be more than one point, but there will be at least one. And then in order for the mean value theorem to exist, we have to have a continuous function between the endpoints, and it has to be differentiable in between those endpoints as well. So it has to be a smooth, connected curve with no corners, cusps, or breaks in it. Okay? All right, and then so we did some examples where we actually set the derivative equal to 0. I think that's about all we did. Yeah. And then we wrapped up with these two problems here. Okay. So, let's continue, and we're going to talk about increasing and decreasing. Okay, consider the following function. This little simple curve that's graphed. As you move from left to right on the graph, the y-coordinates are getting larger. We say the graph is increasing. Notice that the derivative, aka slope of the tangent, is positive for all of these values of x. So if you think of tangent, 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 and I will say that right there it appears it's getting really close to 0, but all of those do have positive slopes. Okay, so if a function is increasing, guess what kind of slopes we should expect? Positive slopes. Okay, consider the following function here. As you move from left to right on the graph, the y-coordinates are getting smaller. We say the graph is decreasing. Notice that the derivative, slope of the tangent, is negative for all of these values. So tangent, 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 all those lines are slanted so that they have negative slopes. And remember back from pre-calc or even algebra 2, when we talk about increasing or decreasing, we're always going from left to right. Okay? So read it from left to right just like we read on a page. Okay, so functions with positive derivatives are increasing. Functions with negative derivatives are decreasing. And the opposite is true. If your function is decreasing, you have negative derivatives. If it's increasing, you have positive derivatives. Okay, so let f be continuous on a closed interval and differentiable in between those two endpoints. If the derivative is greater than 0, what does greater than 0 mean? Positive. At each point on the interval, then f increases on that interval. If the derivative is negative, which means, less than 0, which means negative, at each point on the interval, then f is decreasing on the interval. Okay? Alrighty. Without the use of a calculator, your favorite kind of problem, determine where the function y equals x squared increases and decreases. Okay, now that one's pretty easy because we know what that graph looks like, right? It's just a plain old vanilla parabola with the vertex at 0, 0. And so I can just pretty much go on my knowledge of that graph where it will be increasing and decreasing. So if I'm reading this from left to right, am I starting out increasing or decreasing? Until I get to the vertex, and then I am increasing. What's happening at the vertex? Am I increasing or decreasing? Neither. So it's that transition point. So generally we don't include 0 in the increasing and decreasing.
Would that be like a station point?
Stationary point? Mm-hmm. So y equals x squared is increasing on the interval 0 to infinity and decreasing on the interval negative infinity to 0. So notice we're not including 0 in that because it's neutral. Let's see, up here, this is a way when we don't know what the graph looks like, we'll examine the derivative. So if you think of the derivative of x squared, it's 2x. If I graphed 2x, what would that look like? Okay, a line with a y-intercept of 0 and a slope of 2. Okay, so something like this. So this is the derivative graph. Well, if my graph is positive, what does that mean? The first derivative being positive means that I have positive y coordinates here, right? Well, we just talked about if your derivative is positive, it means the function is increasing. My derivative values, y values, are negative down here. Well, if my first derivative is negative, that means the function was decreasing. So I could also come to this same conclusion by looking at the derivative graph. For all x's less than 0, the derivative is negative, which means my function was decreasing. For all x's greater than 0, my derivative is positive, which means my function was increasing. So sometimes when we don't necessarily know a whole lot about the original function, we'll examine the derivative and determine where it's positive and negative, and that will tell us where the original function was increasing and decreasing. Okay, so what about that point right there? Well, it's 0, 0. So what that tells me is when x is 0, the derivative is 0. Which we knew based on the knowledge of our graph of x squared. Okay, so positive meant increasing, negative meant decreasing. Okay, where is this function increasing and where is it decreasing? Okay, if we solve graphically, we can graph on the calculator and use max and min values to determine where f of x is increasing and decreasing. Let's go ahead and look at that graph while we're mentioning it. So get a graphing calculator. Are y'all hot or is it just me? It's humid, isn't it? Are y'all okay? Humidity's killing me. Alright, so I see that it's a cubic function, so don't you kind of have an image in your head what it's going to look like? Like some version of a cubic function. I do have this minus 4x, so that's going to change it a little bit. And there we go. Okay, so I see several things going on here. If I want to know where it's increasing, remember I'm reading it left to right. So I'm increasing, I'm going uphill until I get to that maximum point. Then I'm decreasing until I get to that minimum point, and then I'm increasing. Okay, so how can I find those values? Yep, go to that second calculate. Let's find that maximum first. So this is where you need a left and a right boundary. Okay. So it looks like negative 1.154 is the x value. I'm going to write this down right here. Increasing from negative infinity to negative 1.154. Decreasing. Okay, I know it's going to start decreasing at this value, negative 1.154. But I've got to figure out where it stops decreasing and starts increasing again. So now I'm going to find that minimum. I need help with the calculator. Oh, it looks like it's 1.154. Okay, then again, it's going to start increasing. So I will say union 1.154 to infinity. Okay, so that's pretty easy on the calculator. But let's talk about if we solve algebraically. We need to first find the derivative, then we will determine where the derivative is positive, which will indicate where the function is increasing, and where the derivative is negative, which will indicate where it's decreasing. Okay, so if I take the derivative, I get this. Okay, I want to know where the function is increasing, so I set that quantity greater than 0. Okay, well if I add 4 to both sides, I get this. If I divide by 3, I get this. Where is x squared bigger than 4/3? Let's talk about what if I took the derivative of this? Okay, the square root of 4/3. So the square root of 1 point something is about 1 point something, right? Okay, so think of a number line. And let's just say I have square root of 4/3, negative square root of 4/3. Okay, so what if I picked a number outside of that? Let's say I picked 2. Okay, if I square 2, is it bigger than 1 1/3? Yes. What if I square 1? 1 squared is not bigger. Similar thing happens over here. Negative 1 squared is not bigger. But if I take negative 2 and square it, that is bigger. Okay, so it's bigger out here, right? Outside of those numbers. So I know that my function would be increasing. X is bigger than square root of 4/3, and x is less than negative square root of 4/3. Which is the same as that decimal that we found, square root of 4/3. Let's double check, but it should be square root of 4 divided by 3. Yes, that was the number that we were finding at the max and mins. Okay, but then where would the derivative be negative? Be negative in between here. And so that would be between the negative square root of 4/3 and the positive square root of 4/3. Okay, so sometimes if we don't have a calculator problem, that's how we'll approach it. We'll have to examine the derivative and see where it's positive and negative. Okay, much easier when you have a simple function like that to use though. Alrighty, this is where we're going to think backwards again. Consider the derivative of these 3 functions. Just think about them for a second. What's the derivative? 3x squared minus 5. What's this one? Oh. And the third one? Okay. Are those functions all identical? No, but they do have the same derivative. Okay, so it quickly becomes clear that any function of this form, y equals x cubed minus 5x plus or minus a constant, will have the same derivative, 3x squared minus 5. So the only way that these differed was that constant that was tacked onto the end, but the derivative of all those constants is 0, so we ended up with the same derivative. Okay, if f prime equals g prime at each point of an interval, then f of x equals g of x plus c, which will stand for some constant, or functions with the same derivative differ by a constant. Okay. Functions with the same derivative differ by a constant. So look at all 3 of these. They had the same derivative. What was the difference in those 3? That little constant that was added or subtracted to the end. Okay. Other than that, they had identical derivatives. Okay, so that leads us to what is an antiderivative. Put your brain in reverse. A function capital F of x is an antiderivative of a function f of x if f prime of x equals f of x for all x in the domain of f. The process of finding an antiderivative is antidifferentiation. How many syllables does that word have? Anti-differentiation. 8 syllables. Anti-differentiation. Okay, so if I told you that I have a function whose derivative is cosine, what would the original function have to be? Sine. So we would say sine plus c, meaning there could have been a number added to the end, but when we took the derivative, it went away. So we don't know what that constant is, so that's what the plus c thing means. So if I told you that I had a derivative of 2x, okay, what would y have to be? X squared, but there might have been a number there, so we just say plus c. Okay, so that would be the antiderivative of this. Okay, so now we're working backwards. Okay, so that leads us into this next one. Find the function f of x whose derivative is sine x and whose graph passes through the point 0, 2. Okay, well, what function has derivative sine? Negative cosine. Okay, so there could be any function here, negative cosine x plus a number. Okay, so you know what cosine graph looks like, right? And if I take the negative, then it just flips it over the x-axis. But then if I add a constant, then it's going to shift it up or down on the graph. So there's an infinite number of graphs it could be. Well, if we're given one point on the graph, it like pinpoints the exact graph, and we can figure out what c is. So it's not like some generic cosine graph. We're actually going to figure out which one, including the constant, that we're dealing with here. Okay, so I would say that if this was the derivative, my original function was negative cosine x plus some number. To find c, we will use the condition that the graph must pass through 0, 2. So what I'm going to do is take 0 for my x, take 2 for my y, and I'm going to sub them in and figure out what the c value is. So f of 0 equals 2 means that I can plug in 0 for the x and 2 for the y. Remember, f of x is another name for y. So my y value goes here, sub in my x value here, and I end up with this equation right here that I'm going to solve for c. Okay, cosine of 0, that's over here. The order pair is 1, 0. So cosine is 1. So I have negative 1 plus c is 2. Add 1 to both sides, c is 3. So we get the function negative cosine x plus 3. So this will be the original function that has this derivative and goes through that point. Questions on that? All right, the last grande question here. All right, find the velocity and position functions of a body falling freely from a height of 0 meters under each of the following set of conditions. The acceleration is 9.8 meters per second squared, and the body falls from rest. The acceleration is 9.8 meters per second squared, and the body is propelled downward with an initial velocity of 1 meter per second. Okay, so let's talk about situation A here. Go back and let's read this first sentence. We want to find velocity and position. Now remember that if I call S of t position, then V of t is S prime, right? And that will be our velocity. Okay, well, if I take the derivative of velocity, what do I get? Acceleration is the derivative of velocity, or the second derivative of position. And that is acceleration. Okay, so we have to keep in mind those relationships here. So that's what we want to find, the velocity and position functions falling freely from a height of 0 meters. If I start from a height of 0 meters, what does that mean? What? It will fall, but it starts at a height of 0, so it's giving me the initial position. So it means at time 0, the position is at 0. So this means that S of 0 equals 0. Does that make sense? At time 0, the position is at 0. There's no height to it at all yet. Okay, the acceleration is 9.8 meters per second squared. There's our acceleration. The body falls from rest. What does that mean? There's no force behind it. So its initial initial velocity or velocity at time 0 is 0. Now that will be different when we propel it downward. Okay, then I won't have an initial velocity of 0. Okay, so I know I'm starting at a height of 0 and I am starting with no velocity. So it's like a rock sitting on the edge of a cliff and we're just going to nudge it over. Okay? All right, so acceleration is 9.8. I'm going to write that as an equation. Acceleration is 9.8. Okay, now here is the deal. Should we use a negative? Why is it 9.8? What's special about that number? Gravity. Okay, what is this gravity doing to our rock? Going downward. So I'm going to use a negative. Okay, now I know it's not listed as negative here, but because I know the acceleration is due to gravity and is pulling it downward, I'm going to use a negative there. What is the antiderivative of acceleration? Velocity. What is the antiderivative of velocity? Position. Okay, the body falls from rest. We already said that means initial velocity is 0. From a height of 0, I already said that means initial position is 0. Okay, so what I'm going to do is I'm going to take this only equation that I have, this little baby equation, A of t is negative 9.8, and I'm going to work backwards to find its velocity. Okay, if this is the derivative, what did I start with before I took the derivative? Yeah, just the variable, right? So negative 9.8, since I started using t, I'll stick with t. It's fine if you want to use x throughout also. Okay, that had to be the original function to give me that derivative. But there could have been a number. Okay, so now this is where I'm going to take this equation, v of 0 equals 0. That tells me that the order pair 0, 0 is on the velocity function. So x is 0 and y is 0. So I'm going to plug in 0 for y, 0 for x, which is time here, plus c. 0 equals 0 plus c, so c is 0. So what that tells me is my velocity function is just negative 9.8 t with no constant, or a constant of 0. Everybody okay with that? All right, well now I'm going to keep working backwards because remember I wanted to find velocity and position function, so I found velocity. But I'm going to keep working backwards and I'm going to take this velocity function and figure out what position must have been. Okay, so position of t, if this is the derivative, you gotta put your thinking cap on, what did I start with? Say that again?
T to the negative 9.8.
Ooh, no. 0.8 t squared?
No, 9.8 t squared.
Okay, keep thinking. Gracie, what?
4.9 t
Oh. Can I throw a negative in there? Where did she get 4.9? Yeah, remember whatever was here got multiplied by 2. All right, so you did recognize when y'all were throwing around ideas, you knew that we needed a t squared. Okay, so I added 1 to that exponent, which is the opposite of what we usually do, and I had to divide the coefficient by 2, which is the opposite of what we use. So we're literally working backwards. So I added 1 to the exponent, but then had to divide that by the 2. Yes?
So how do you know that needs to be a t squared and not like t to the negative 9.8?
Okay, because if that had been t to the negative 9.8, then when I brought that down, t would be to the negative 19.8. I would have had to subtract 1 from the exponent. Okay, good question there. All right, any other questions about how we got that negative 4.9? Okay, so now that I know the setup, then I'm going to go back and take this point that we knew, initial position was 0, so when x or t is 0, y is 0. So 0 equals negative 4.90 squared plus c. 0 equals 0 plus c. C again is 0. So that means that my position function was just negative 4.9 t squared. Question. Okay, so part B changes it up some. So that's pretty simple because we got 0 for all the c's. So let's see what happens when we change some stuff. Okay, acceleration is the same. So we'll still use a of t equals negative 9.8. From a height of 0 meters. So it still is falling from a height of 0. So that means initial position was 0. When time was 0, position was 0. But this one is propelled downward with an initial velocity of 1. Okay, how am I going to write that? Initial velocity of 1. V of 0 equals, I'm going to use a negative 1 because it's downward. So negative indicating direction. Is everybody okay with that? All right, so we're going to do the same thing. I'm going to work backwards from acceleration, and I know that v of t is negative 9.8 t plus maybe a constant. Okay, well, I know that v of 0 is negative 1. So that means when t is 0, velocity is negative 1. So negative 1 equals negative 9.8 times 0 plus c. And what is my c value now? Negative 1. That it's being propelled downward. So this one, remember, just fell from rest. So like it got bumped or kicked or whatever. It just fell off the cliff. But this one, we're actually like throwing it or whatever. Something is propelling it. So now my velocity function is negative 9.8 t minus 1. Okay, so we're going to work backwards some more to find our position function. So if this was the derivative, what did I start with? Well, we already figured out the negative 4.9 t squared. But what about the minus 1? Minus x or minus t. And then there still could have been a constant there. Okay, so what information do we have? I know that s of 0 equals 0. So when t is 0, position is 0. And what will c equal? Just 0. So that means the position function was negative 4.9t squared minus t. Question. Okay. All right, let's go back and look at that number 40 again now that we talked a little bit more about increase, decrease. Okay, so part B. Yes, sir. Next Friday. What is that, the 15th or something? Yeah, next Friday. Okay. Okay, all right, bye. Okay, so part B of this problem says, we still want these two conditions to hold true. So these are going to be part of all of them. So I need an order pair 2, 3. Who's showing a movie? Okay, there's my order pair 2, 3. Remember, I have a derivative of 0 there. But part B says, I'm not going to write this down. Let's just look at it here. Part B says the derivative is negative for x is less than 2. The derivative is positive for x is greater than 2. What is this going to look like? A what? Yeah, an upward parabola. So in this case, I should have graphed it, giving myself more room. But in this case, I have a parabola that looks like that. Negative slope, negative derivative, positive slope, positive derivative to the right. Does that make sense? Okay, part C. So I still have that same ordered pair, and there's still a slope of 0 there. The derivative is less than 0 for x not equal to 2. So that means everywhere on the graph, the derivative is negative. Except here, where the derivative is 0. How can I have negative slope everywhere, but I have a little slope of 0 right there? It is what we call a shelf point. What's the graph going to look like? Cubic, yes. So it's going to come down, decreasing, little bitty moment of slope of 0, but then it's going to be decreasing again. So something like a negative cubic curve would work there. Negative slope, negative slope, negative slope, little momentary piece, little segment where it's 0, then negative slope, negative slope, negative slope. So then D is the opposite. Now the slope is positive everywhere except this point. So what's that going to look like? How can I have a slope of 0 right there, but positive slope everywhere else? Increasing everywhere else? Okay, like a normal cubic curve, something like that. Okay. All right, so you have the rest of the block to finish up those problems. They are on your agenda, and I'll just help as you need help.